Perfect. So let's talk about glycolysis. Glycolysis. Finally, explain. So, in glycolysis, we start with the glucose. Molecule, which looks like this. And then an enzyme called hexokinase comes with some ATP and phosphorylates this compound. So it's going to remove that H, and now it's going to be substituted for this PO3 2 minus. So ATP means just literally 3 phosphates. So but we lost 1, so now we lost 1, so now we have 2, and this is why we got now ADP. Yeah. So that's the first step. By the way, I'm just not writing the hydrogens because you guys can tell it's a little too much. Alright, so what happens now? We have a new enzyme called the enzyme is called phosphoglucose isomerase. Now what that does is actually comes and cuts this bond. Actually, I'll change different color here. It comes and cuts this bond. So when that does that, just rewriting our sugar molecule. I want you guys to get every single detail of this glycolysis. So we're gonna cut that, and since we are cutting it, the enzyme actually can cut it from this end of the bond or this end of the bond. So let's say we have a bond, let's say we have this bond right here, right? These two bonds. If I could cut it here, or I could cut it here. If I cut it about the left, it makes a carbon, this carbon would make it negative, and the one on the right we have a partially positively charged, so it would make it a carbocation, right? And just for visual, I'm still leaving the bond there, but now it's just the carbocation, right? So it's a new notation I come up with, so you can visually see what's going on. So if I cut it here to the, I'm cutting it here on the right side. So now this carbon on the left, it's a carbocation, and the carbon to the right is partially negative. Cool. So that's what's gonna happen here. So it's going to make this a carbocation on this oxygen, and so that means that this carbon here is gonna become negative. So that's actually going to look like this. Like the carbon here is partially negative, and this just has a carbocation here, the oxygen. So I'm also going to cut the hydrogen that's in here, and I'm gonna cut it right here. So if I do that, that means that the hydrogen is gonna get a partially, it's just gonna be a regular H plus hydrogen, right? So now it's gonna be just floating here in the air, just, and then this carbon here, it's missing a hydrogen. So actually I should write the rest of the hydrogens so you guys don't get confused. So now this oxygen, this negative is going to grab this oxygen now, because it's a carbocation, it's positively charged oxygen, so it grabs there, and then guess what, this hydrogen is positively charged and this carbon is negatively charged, so now this is going to attack that, and it's going to make this new ring here. So and now we have this CH2. Dun, dun, dun. Sorry, there's an H here, right? So now we get this CH2OH. Great. Perfect. And this is called fructose 6-phosphate. It's a fructose 6-phosphate. So now we're gonna get this new enzyme, and at this point phosphoglucose isomerase comes, again with some ATP, and it's gonna do the same thing we just did above, but now it's gonna do it here. So that phosphorylates that. Okay. Perfect. And of course, we had ATP, it gave it here, so now it leaves with some ADP. because ATP lost one phos. It lost this group, so now it's just ATP. Cool. Now that we're here, we're going to unfold this into what is called a fissure projection. And how that happens is the enzyme comes and it actually cuts this bond about right here. What does that mean? It means that now this oxygen is going to be partially it's going to be positive now, and then the carbon here is going to be negative. Okay, so we cut the ring now, so that's why we have this weird looking ring now. So we cut it, but okay. So now this, imagine this rope is like can swing around and hit this carbon here. So if it hits it, it's gonna break this hydrogen. So if it breaks that hydrogen, we have we're gonna have this floating hydrogen positive. This carbon here is gonna be at the instant that it hits it, it becomes negative. So it's just like a kind of like it closes, and then that's what we get this, and then this negative disappears the moment this bond attaches, so you get this double bond there. And then let's keep going here. Forgot to write this. It's just a lot of drawing, so I might miss a little hydrogen, but that's okay. So this free hydrogen here comes. This is just another CH2, of course, right? PO3 2 minus. Okay, CH2 PO3 2 minus, and this is going to now attach here. Perfect. So we end up with something looking like this. So we get this CH2O PO3 2 minus, we get this, then we got this OH here, we get this OH going up, and of course, you know, there's the hydrogens here, and then this, now this right here makes a CH bond, here's the OH bond, and we get that. It looks kind of ugly right now, but now you can see now the nice fissure projection. So let's rotate this way. So now we get this nice fissure projection. It's going to look like that now. Perfect. And of course, you know, this is just a carbon. Chun, chun, chun. So we get this nice Fisher projection. Beautiful. So what's gonna happen here? Let's look at this. There comes a new enzyme. This enzyme is called aldolase. And this is cool. Enzymes just come, they lock, or you know, they may be flexible, and this is why they're unique. They cut at a certain specific place. That's what enzymes do. And then I could cut it here, or I could cut it here. So I'm gonna cut it right here. This enzyme cuts about right there. What happens now? Okay. This carbon's negatively charged now. Okay, don't forget your negative charge here. Okay, and then this carbon is positively charged. It's a carbocation. So we cut okay. So we cut it. And now this rope or this bond wants to swing, and it's gonna swing most likely to this negatively charged oxygen, so it swings this way. And let me redraw this hydrogen just so you guys can visualize what happens. The moment it hits this hydrogen, it breaks it here. So when it breaks it, this bond, it breaks it will make this oxygen negatively charged at that instant. So that's why this carbon makes this double bond with the oxygen. But now we have this free hydrogen. Yes. So look at what happens here. We have now two molecules. We have this molecule, and don't forget about this other molecule. But now we have this free hydrogen, so it's going to come, this electron is gonna wanna grab this hydrogen. So now we have another molecule, so we make two molecules, and this is the other molecule. The H now here. Yeah, so we have this molecule, and we have this other molecule now. Cool. And this molecule is called glyceraldehyde. Perfect. So these go back and forth, you know, and turn into glyceraldehyde. So let's talk about now what happens to that molecule. We have now an enzyme called glyceraldehyde 3-phosphate dehydrogenase. And let's look at the molecule that we have. So let's draw it. Just rewriting the same molecule that we had. Oh wait, sorry, let's not. I'm getting a little ahead. So let me actually erase that, because that's what we're gonna make after this enzyme comes. So we actually have this, which is this is what we have. So this enzyme actually comes and cuts it here. And this is very special, because if we cut it about there, it's gonna make this hydrogen negative now. So we get this negative hydrogen, which is called a hydride ion. And this finally explains for the first time why you can have a negatively charged hydrogen, and this carbon, it's positively charged. And this is why this theory is so important. By the way, this theory, I call it enzyme bond or rope theory, because we're making these bonds behave like, like if there's some kind of rope, which is kind of what we do with the bonds, right? They kind of like attach this carbon to this carbon is attached kind of like a rope, right? We just call it a bond, but that's essentially what's happening. So at this stage, we have some phosphate and some NAD plus, and then this NAD plus is gonna want to grab to this hydride ion, and as a product, this is going to make NaGH. So this phosphate group is negatively charged, so it's going to come and grab this positively charged carbocation or carbon, and now this is going to make this. Yeah. There comes another enzyme. It's called phosphoglycerate kinase. But this one comes with some ADP. So guess what it does? It grabs that phosphate, and you finally make some ATP. Ooh, we make some energy here. So when we remove that, we get this molecule. Don't forget your negative charge there. Okay. So let's now, I think this is called 3 phosphoglycerate. And let's not rewrite it. Let's rewrite it like this. Just for visuals. Just rewriting this OH into this. And then I'm going to draw this CH2O and this PO3 2 minus. So now this enzyme comes and it's gonna cut it right here, but it's also going to cut it right here. This is why enzymes are so special. It would take like maybe a long time for this to happen, but enzymes just come, cut them. They come and break these molecules, and this is why they bend and break these bonds. That's essentially what these enzymes are really doing. Very fascinating. So if I break it here, it's gonna make this oxygen positive. Not positive, right? Because my theory says that if you cut it about here, then this becomes negatively charged, right? So it has an extra, you would say it has an extra, so we have an extra lone pair, so it becomes negative. And then this is just a normal hydrogen, right? Just H plus. Same thing here. It's gonna make this negative charge there, and then it's gonna add positive charge to this PO3. Of course, this would turn into like a -1 charge, but what we want to do is just this hydrogen is going to bind now to this oxygen. Positive and negative attract, and same thing is going to happen here. This negative is going to bind with this positive now, and we're going to end with this neo. Which is pretty cool. So what it does is it rearranges, the enzyme literally rearranges this molecule. It's crazy what it's doing. And I'm just going to rewrite just for simplicity so you can see what happens on the next step. So the enzyme comes and cuts it right here, and it's going to also cut it right here. Now this carbon becomes positively charged, and this hydrogen is now negative. So we get a hydride again. Now we know we cut about the right, it'd be an H plus, but we cut about the left. It's not left or right, so it's like you cut close, the close become it's a negative. So same here, the this cut happens close to the carbon, so it's gonna be negatively, and then this hydrogen is not gonna be positively charged. So it'd be like a so this hydride now comes and binds to the OH. Yes, and then this positive now binds to this negatively charged carbon. So what happens now is we get this extra, this now becomes this bond with that negative, so it makes a double bond now. Cool, right? And then we have as a product some H2O. Yeah, we get some water in this product. So don't forget to draw the oxygen here, right? Let's not forget about that. So cool, we find some oxygen. And then finally we have pyruvate kinase, or I don't know how to say kinase or whatever. So he's literally all he's gonna do is it comes with some ADP. It grabs that, so it makes another ATP. So now we have two ATPs. That we made, and this cycle happens twice. It happens twice, right? Because remember that we cut this molecule in two, so we made two molecules, so the process happens twice. So we actually get 4 ATPs, and we invested 2 ATPs, so we get a net of 2 ATPs and glycolysis. So it just comes, grabs some ATPs, and then the last part is the molecule it's just chemistry now. It just goes through tautomerization, and then we finally get our pyruvate molecule, which is literally just this. If that confuses you, if you guys like this explanation, I can go over the last step on how to go from there to that. But this is just chemistry, and this is the same thing as writing something like this. So thank you guys for watching. So I actually invented this theory to explain glycolysis. and how enzymes work and what kind of work they do. So right now I'm currently trying to go to med school. So any support, I really appreciate you guys subscribing to my channel. So I graduated from UC Berkeley, and as an electrical engineer and a computer science degree. So I was happily being able to apply my some knowledge in just a little bit that I know, but hopefully I can contribute to um, a better understanding of these complex systems and enzymes and make life a better place. And thank you. Oh, actually, before I cut this, there's one thing I wanted to go over. Um, this theory is actually so important because when we see this carbocation, it actually has the shape of I'm sure you guys seen this in chemistry. So it has this lobe, right? And it doesn't make sense what that is there. So this theory, it actually explains why that happens. So let's say we have some CH4, and let's say we cut it about here. So if we cut it about there, it's gonna have this negative hydrogen now, and then pretend this bond, now it's a broken bond, right? So the reason why we have this s and s orbitals is because this s orbitals, like let's say like hydrogen has an s orbital, because the electron could flow evenly around it. But when you cut this bond, like imagine, let's say we have this marble attached to some rope, okay? Like that. Okay. Just pretend these are, just for simplicity, these are just marbles. So if we cut this rope, if pretend this is an actual rope, so I started thinking in ropes, like, so if I cut this rope, what's gonna want to happen to this rope? It's obviously gonna want to come down, right? It's gonna want to come down like this, like that, and eventually is going to form this pattern of this pattern like this, and of course is gonna keep falling. Like pretend this is the tip of the rope, so falls, right? And it's gonna want to keep falling, but eventually this rope is gonna get pulled back up, right? And it does the same thing because now it's loose. So now it's loose, so it's like a proton just being kicked by this negative charges, positive charges, just being kicked around, and it becomes this shape. So this is why it gets this shape. This is why this theory is actually so important. It explains the hydrogen ion, It explains why we get this special shape, and more importantly now, it's now we can actually, with this theory, we can now design enzymes, and we can artificially design enzymes with electric charges or electrons and protons, and use them as like some way to grab a molecule. Wow, this is going to open a new field where it's just, and I'm sure we already use these electric charges to, as a catalyst, but now we're going to be able to do crazy things. So thank you guys for watching, and I'm very fascinated about this, and um, any support, or if anybody wants to donate for my med school, I'll really appreciate it. Uh, Come up with a link or something like that, or I mean, I'll just appreciate it at a like and subscribe. So thank you.